Welcome back, everybody. I'm here in the Chapter 12 lecture note outline packet on the first page, and today we're going to start learning about solutions. So we'll talk about solutions over a few videos, and in this first lesson, we're going to learn the basics about what a solution is, some terminology about solutions, and then we'll learn some of the other aspects like concentration, all that in the next lesson. So this lesson is a lot of conceptual material, and then in the next lesson, we'll do some sort of practical quantitative aspects with solutions. So with that, let's get started learning about solutions and the terms that we use to describe them. So what exactly is a solution? A solution is a homogeneous mixture between a dissolved substance and a liquid. We call the dissolved substance a solute, and we call the liquid that does the dissolving the solvent. So a solution consists of both a solute and a solvent. Later, when we start doing calculations with solutions, it becomes important for us to denote the mass of a solution. Now remember, a solution consists of both the solute and the solvent. So remember, if we want to find the mass of a solution, we have to add together both of these. The mass of a solution is equal to the mass of the solute plus the mass of the solvent. Now, sometimes a particular solute does not completely dissolve in the solvent. In this case, we don't have a solution necessarily. We have what we call a suspension. A suspension is a heterogeneous mixture between a solid phase and a liquid phase. Now, we're also going to discuss the solubility of different materials in other things. We'll talk about the solubility of solids, and the terms we'll use to describe that are insoluble and soluble. Insoluble refers to a solid material that does not dissolve in a liquid, whereas soluble is the opposite. It refers to a solid that does dissolve in a liquid. Solutions can also be prepared from two or more liquids. When we're describing the ability of liquids to mix together, we use the terminology for miscibility. Miscibility refers to liquids either mixing together completely or not. Miscible liquids are liquids that mix completely, whereas immiscible liquids do not mix completely. An example of liquids which are immiscible would be oil and water. Sometimes we also use the word suspension to refer to a mixture of immiscible liquids, much in the same way as we refer to a solid and a liquid phase that do not mix completely. So we can use the term suspension for either of these. Now that we know some of the basic terminology about solutions and solubility, let's go to the next page where we'll learn why some solutes are soluble in certain solvents, whereas others are not. So first, to understand solubility, it's helpful if we divide solutions up into different categories based on what's actually doing the dissolving and what's being dissolved. In general, there are three types of solutions that we will look at: ionic solutions, acid solutions, and molecular solutions. Let's look at each of these types of solutions and see how it's actually working down at a molecular level. Now, for each of these types of solutions, what I want you to think about in each case is what's actually causing the solute to dissolve in that solvent. I'll highlight this principle over and over when we go through different types of solutions. The idea is that like dissolves like. And what I mean by that is things that are similar to one another will likely dissolve each other. So many of the things that we look at here are going to be what is similar or what is different. And we'll focus a lot on the polarity of different things. So if we have a molecule that's very polar, it will likely dissolve another molecule that is also polar. But it's unlikely that a non-polar molecule would dissolve a polar one. That's this principle, like dissolves like. All right, so let's go take a look at this first type of solution, ionic solutions. Now, are ionic compounds polar or are they nonpolar? So remember, an ionic compound is one that consists of a cation, that is usually a metal, and an anion, that is usually a nonmetal. So if you identify this as a polar substance, you're correct. It's definitely polar because we have two opposite charges here, two opposite poles, a positive one and a negative one. So would you think then that an ionic compound, being polar, would likely dissolve in a solvent that is nonpolar or polar? Well, if you said polar, that's definitely correct. You're using the principle of like dissolves like to determine that. Since an ionic compound is polar, it would make sense that if it were to dissolve in a solvent, that solvent would also have to be polar. To explain this principle like dissolves like and why it works, we can use an example like sodium chloride. Sodium chloride, also known as table salt, dissolves readily in water. And that's because water is polar and so is sodium chloride. Now, when you take some table salt in your hand and you look at it, you see it's solid white. That's because all the different ions, all the sodium and the chloride ions, are there clumped together in their massive crystal structure. Now, when we put that solid sodium chloride into water and we stir it around, something happens. The molecules of water separate the ions that are in the sodium chloride into individual cations and anions, like in the diagram I have here below. The water molecules surround each of these ions. We call that a solvation shell, and we write it out as a chemical equation like this. We take the solid sodium chloride as an example, and we place it into water, and the ions are separated from one another, so they're no longer connected directly without anything in between them. So we have the sodium cation, and we write aqueous to show that it is surrounded or hydrated around it in a solvation shell of water. We also have the chloride anion, which is also solvated by water. So when we write sodium chloride with the aqueous symbol next to it, what we're really meaning is that the sodium and the chloride ions are separated from one another, and each of those is actually aqueous itself. Now, look at this diagram I have below where I'm showing the two-dimensional representation of the solvation shell. You can imagine this in 3 dimensions with actually 6 water molecules surrounding each of these ions. Do you notice a particular pattern to the solvation shell? And why do you think that is? Well, that's right. If you actually look at the water molecules, they're organized around each of these ions in a particular pattern. We have the delta plus end of the polar water molecule surrounding the negative chloride ion, whereas sodium, which is positively charged, is being surrounded by the negative, or delta negative end, I should say, of the water molecule. Now, if water was nonpolar, it wouldn't do this. It wouldn't line itself up around these ions. And in fact, it wouldn't actually be able to break up the crystal lattice structure, which holds together the sodium and the chloride anions. So if you take solid sodium chloride and you put it into a nonpolar solvent, you see all of the sodium chloride sitting there because they're all stuck together still. But when you put it into water and it dissolves, all of the water molecules separate that crystal lattice structure, and that's why it appears to be invisible. All right, so now let's go to the next page and look at a few more types of solutions. Acid solutions are solutions in which we dissolve an acid in water. Now, because we haven't talked about acid-base chemistry yet, the word acid is a little bit mysterious at this point. For now, what I want you to know is that an acid we will always represent with an H, or a hydrogen atom, as the first element in the formula. So if we ever see that H first, we're going to assume it's an acid. So here are some examples. We have hydrochloric acid, which is HCl, hydrobromic acid, which is HBr, HI, which is hydroiodic acid. We also have a few other types of acids where there are more than one proton. So for example, we can have sulfuric acid, which has 2 protons. This is called a diprotic acid because it has 2 protons, and the prefix di means 2. We can also have phosphoric acid, which has 3 protons. You could call this a triprotic acid, but you could also call it a polyprotic acid because there's 3 or more of those protons on the front. Now, if diprotic acids have 2 protons and polyprotic or triprotic has 3 protons or more, what would we refer to these molecules in the beginning here, HCl, HBr, and HI? Well, that's right, we would call them monoprotic acids. Now, it turns out that acids are very polar. They're so polar, in fact, that they behave almost exactly like ionic compounds in solution. So because they are so polar, they ionize readily in polar liquids like water. When they do this, they release H+ ions, forming the solutions that result. Let's take a look at a few examples. We'll look at a monoprotic acid, a diprotic acid, and phosphoric acid. In water, hydrochloric acid ionizes into a proton, which is aqueous, and a chloride anion, which is also aqueous. In a similar way, sulfuric acid also ionizes, but in this case we have two protons which are released into this aqueous environment instead of one proton as in the monoprotic acid HCl. Now, what do you think phosphoric acid does with its three protons? Well, that's right, because it's triprotic, it releases all three of those protons into the aqueous environment. Now, what does this solvated proton actually look like, this H plus ion with water molecules surrounding it? Well, you might remember the hydrogen bond that we discussed in the chapter on intermolecular forces, and you might remember that hydrogen bonds are one of the strongest of the intermolecular forces, and they happen when you have a slightly positive proton near, say, an oxygen that is delta negative. Well, we have here a situation that's much like that, except we have a completely positive proton instead of a partially positive one. So what happens is the water molecule is very strongly attracted at that oxygen to that positively charged proton. What ends up happening is we end up making a complete covalent bond between that oxygen and the proton. We call this H3O a hydronium molecule, and it represents the solvated proton H plus with the AQ after it. When we write H plus AQ, what we really mean is hydronium, or H3O plus. So we have polar molecules like salts and acids which readily dissolve in polar solvents like water. What about everything else? We call these molecular solutions. Solutions that are made up of not ionic compounds or acids, but molecules, things that involve all nonmetals bonding together in compounds. Now, predicting the solubility of molecular compounds is not very straightforward. That's because there's a lot of variability in this class of compounds that we're saying is molecular. There's a huge variation of things ranging from like petroleum products, which are all just carbon and hydrogen bonded together, versus things like carbohydrates, which have carbon, oxygen, and hydrogen, and sometimes even nitrogen, all in the same molecule. So there's a lot of variation in it, and for that reason, we get a lot of different solubility properties. Now, we're not going to go into too much detail here other than dividing molecular compounds into two big categories and then trying to make some predictions based on the category that a particular molecule is in on whether or not it would be soluble in water. So let's say that molecular compounds can be either those that form hydrogen bonds or those that cannot form hydrogen bonds. Now, we know how to look at a molecule and determine if it has hydrogen bonds or not, so that part's easy. Now, we can say that molecules that form hydrogen bonds are a lot like water, right? Because water also forms hydrogen bonds. So if a molecular compound is one that can form hydrogen bonds, we say that it's more likely to be soluble in water. Now, molecular compounds that cannot form hydrogen bonds are less likely to be soluble in water. Now, some molecules, like the carbohydrate I've drawn below, this is glucose, by the way, form many hydrogen bonds at once. So glucose, the molecule that I've drawn here, has a bunch of carbon atoms in it. So it's 1, 2, 3, 4, 5. These are all different carbon atoms here, and there's also one out here. But it also consists of an oxygen bonded to a hydrogen at many different locations. So we have hydrogen bonding that can form here, 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 and here. We can also form hydrogen bonds at this position to water because we have a delta negative oxygen that can be attracted to the delta positive on water. So we can form many different hydrogen bonds on glucose, and glucose readily dissolves in water. Now, if you take all of these oxygen atoms off, so each of these, but you leave this one that is in this ring here in place, that molecule actually doesn't dissolve in water because it doesn't form hydrogen bonds at all of those different locations. And we increase the solubility by having more of these oxygen atoms on the ring. The more you take away from this, the less soluble it is in water. So that's the basic idea with molecular solutions. Just like ionic solutions and acidic solutions, we're talking about like dissolves like. Now, with ionic solutions, we have a polar molecule already, so ionic solutions are always formed between an ionic compound and a polar solvent. Acid solutions are also polar because we have acids, which are very polar, and those dissolve readily in also polar solvents. Now, with molecular solutions, we can get molecules that form hydrogen bonds. Those will dissolve in water. and those that can't form hydrogen bonds won't dissolve in water. What would they dissolve in? Well, that's right. Molecular compounds that do not dissolve in water and are nonpolar would dissolve in nonpolar solvents. If you ever want to make a prediction about whether something would dissolve in a particular liquid, just ask the question, is it like that liquid or is it very unlike that liquid? If it's very similar to it in terms of its polarity or structure, likely it will dissolve in it. But if it's not like it very much, like it's not very polar or doesn't form the same types of intermolecular forces, likely it's not going to be soluble in that solvent. Okay, so now let's go to the next page and learn a little bit more about solubility, specifically a few terms referring to saturation. So far, we've been talking about solubility and the ability for different liquids to dissolve a given solute based on their intermolecular forces. We also have terms that are used to describe the state at which a solution is in based on how much of the solute is actually dissolved in it at a given time. These terms are unsaturated, saturated, and supersaturated. Let's go through each one of these and see what they mean. Let's start by talking about unsaturated solutions. The word unsaturated means that it is not full yet, so we can put more stuff in it. So if we're talking about an unsaturated solution, what that means is we can dissolve more solute in it before it fills up. So a test for an unsaturated solution would be take a liquid that has maybe some of the solute dissolved in it and put a little more in. If we stir it around and that additional solute dissolves, that means that that solution was unsaturated because we can dissolve more in it. Now let's compare that with another case. What if I take some solute and I put it inside of this test tube and I stir it around and it doesn't dissolve? So after some time of stirring it, we see a bunch sitting at the bottom. What does that mean about the saturation? Well, it means we can't dissolve any more in it. It's full of that solute. We describe this as saturated. A saturated solution is a solution in which no additional solute can dissolve. Okay, now we get to the third case. The third case is a very special case. It's called a supersaturated solution. A supersaturated solution is a solution where we have actually dissolved more of the solute than should be possible at that temperature. The way this works is we take a solution and we warm it up. Now, when we warm up a solution, we increase the amount of solute that can be dissolved at the temperature it's at. Because we've raised the temperature, more dissolves in it. Now, if we very carefully cool that solution down without agitating it, the solute will stay in that solution. It won't fall out of it until it's agitated. When it's agitated, however, all of a sudden a bunch of crystals will drop out of solution. If this is done carefully, we can grow very nice crystals in this way. So a supersaturated solution is one in which we dissolved more solute because we were at a higher temperature, and then we carefully cooled it down to below that solubility point for that particular solute. Because more solute is currently dissolved in that solvent than should be possible at the temperature, no more solute would dissolve in it if we added some. In fact, if we added some solute to a supersaturated solution, immediately a bunch of new crystals would grow around the solute that we added. Sometimes these are called seed crystals because they are placed in a supersaturated solution in order to grow crystals of a specific type around those that we added. So now that we have an introduction to solutions and the terms describing solubility and the way that solutions form, next time what we're going to talk about is concentration and the effect of temperature and pressure on solubility as well. So we'll learn how to do some calculations and learn some different new types of units that we haven't seen before. So with that, I'm going to end this lesson. Please let me know if you have any questions, and I will see you soon.